So again, we return to our equivalent circuits. We have a long string of devices and energy is flowing from left to right. And we're going to define a port plane somewhere along that stream. And everything to the left we're going to replace as an equivalent source, and everything to the right has a load whose impedance is equal to the input impedance of everything to the right. And we found from this equivalent circuit we can calculate the voltage and current at this port plane and thus determine the rate at which energy is flowing across that port plane from left to right. And of course, then by conservation of energy, we find that the rate of energy coming out of this equivalent source, the delivered power, must be equal to the rate of energy flowing into the load, this absorbed power. And the result is given here. So this rate of energy flow, this power, the delivered power from the source and the absorbed power from the load, depends then on the entire circuit. I can't say from the source what the delivered power should be, nor can I say from the load what the absorbed power should be. I need to go through and look at the entire circuit before we can calculate the rate at which energy crosses from left to right. This is in contrast to another power value that we talked about, and that is the available power of the source. Remember, the available power of the source is a value that depends only on the source itself. The value, if the available power is 600 milliwatts, it's 600 milliwatts, regardless of what it's connected to. We could have that source sitting in a desk drawer and its available power would still be 600 milliwatts. Now, that doesn't mean that it's delivering 600 milliwatts. If it's connected to nothing, it's delivering 0. And of course, this is an important point then about the relationship between the delivered power of a source and its available power. Delivered power is the rate at which the source is delivering energy. And again, that depends on what it's connected to in addition to itself. The available power then is the maximum rate at which it can absorb energy. Generally speaking, the delivered power will not be equal to that available power. The delivered power will be less than the available power. Of course, it can't be more than the available power since the available power is the theoretical maximum. The delivered power will be less than or equal to that available power. And so we might have a source that has, a large amount of available power, a source that has, 6 watts of available power. But we connect it to a load, and depending on the value of that load, when we go through and do our math, it may be that the power absorbed by that load may not be, will not only not be 6 watts, it might be 6 microwatts. And of course, that means that the source is delivering energy at a rate of 6 microwatts. Even though its available power is 6 watts, it's delivering energy at simply at 1/1,000,000th of that available power. Again, this depends on the load itself. So if we want the source to deliver energy at the rate that's equal to its available power, we need to change our source. We need to alter our source such that the source impedance is numerically equal to the complex conjugate of the source impedance, or the load impedance rather, is the complex conjugate of the source impedance. If ZL is equal to the complex conjugate of ZG, then under that condition, and only under that condition, will the rate of energy flow out of the source be equal to its available power. The available power of the source then will be absorbed by the load for this conjugate match condition. Now, the problem with this idea of a conjugate match and extracting all the available power comes really to one that is pragmatic. What's practical about it? And we make it sound like, we just fiddle with the load until we get a load that's the complex conjugate, and then the power, the source will deliver power at a rate equal to its available power. But in a real sense, we can't fiddle with the load, because that load is the input impedance to a useful device. It's an equivalent circuit. It's just not a big lumped, impedance that we can, add some resistance or subtract some reactance to it and tune our load impedance so it's the complex conjugate. It's the equivalent circuit of something useful. And if we were to change that input impedance, we change that useful device. We've designed a device that does something useful to us, and its input impedance turns out to be, is what it is. And so how do we go through and change the input impedance of a useful device without making that device less useful? And so it seems like this, even though an interesting concept of conjugate match, it is one that is not particularly useful, not very pragmatic. It's really more of an academic problem. But it turns out there's a solution to this. The solution then is to insert a two-port device between our source and our load. And this two-port network acts as an impedance transformer, we'll see, that transforms the load impedance or the source impedance in a way that results in a conjugate match, and therefore the power delivered by the source will be equal to its available power. Notice in this case we have not altered the load impedance at all. What we've done is transform the load impedance into a new impedance, one where a conjugate match exists, and therefore delivered power is available to the load. And also, as we shall see, we can make it such that the absorbed power is equal to the available power. All of the available power of the source is absorbed by the load if we insert a proper two-port device. And we do this without having to alter the source itself, this useful device, nor alter the load itself, again, the input impedance of some other useful device. And this is the ideal equation with respect to power transfer along our microwave or radio systems. We want all of the available power to the left to be delivered and thus absorbed to the right. We want to maximize the rate at which energy is flowing down our system. So the question is, what is this two-port device? We're going to call it a matching network, and let's see if we can understand what a matching network actually does. So the key thing here is in our circuit, we start with the assumption that our load impedance is not the complex conjugate of the source impedance. So how could we have, again, a case where all of the available power of the source is delivered? Well, to have all available power delivered, it's not a statement of saying that the load impedance must be the complex conjugate of ZG. Since we place a two-port matching network between the source and the load, what we're really saying to create a conjugate match is that this two-port matching network must transform the original load impedance into a new impedance, and that input impedance then is the complex conjugate of the source that is connected to. So we look at this two-port device and we interpret it as an impedance transformer, one that transforms the load impedance, which was not equal to the complex conjugate, into a new impedance, an input impedance, which is equal to the complex conjugate of the source. Once we've done that, we have established a conjugate match at the input port of our matching network, and we will extract energy from our source at a rate equal to its available power. Here then is essentially the schematic that represents this transformation. We start with the load ZL that is not equal to the complex conjugate of our source ZG, but we put in a two-port network that transforms that impedance ZL into an input impedance now, which is numerically equal to the complex conjugate then of this source. Because of that, the rate at energy flow across this interface, across this port into the matching network will be equal to the available power then of that source. Again, the input impedance here, remember, is the equivalent circuit for the entire circuit to the left of this port plane. In other words, the input impedance represents then not only the matching network, but also this load. The Zn depends on the design of the matching network and depends on ZL. And so therefore we're going to have to design the matching network so that it transforms a specific value of ZL to a specific value of Zn, that is the complex conjugate of a specific value Zg. Now, what happens to all of this power that's delivered by the source? The available power of the source now is delivered by this source. Where does that energy go? Well, it is absorbed by the input impedance. Now, what does it mean to say it's absorbed by the input impedance? Again, we talked about this earlier. This is where students sometimes misinterpret what is happening now. Oftentimes, students assume that if it's absorbed by the input impedance, and the input impedance is right here by the input of the two-port matching network, that somehow the matching network absorbs all of that energy. But remember, if we say in general, if a two-port device attached to a load has an equivalent circuit and input impedance and it absorbs energy, we're saying it's absorbed by all of the circuit that input impedance represents. Somewhere in the matching network and the load, or the combination of the two, all of this delivered power is being absorbed. We can't say right now how much is absorbed in one place and how much in the other. It could be that half's in the matching network and half's in the load, or 10% in the matching network and 90% of the load, or vice versa. However, there is one condition where we can say how much of the power is absorbed by the matching network and how much is absorbed by the load. And this is a very important condition and a very useful one, and one that we will now attach to a matching network. Because, of course, we don't want the power delivered by the source to be absorbed by the two-port device. The whole point is to try to get that delivered power to be absorbed by the load. So how do we make sure that the power absorbed by the input impedance is absorbed by the load only? In other words, how do we ensure that the two-port matching networks absorbs no energy at all? Well, we know how to build a two-port network so that it's such that it absorbs no energy. We build that two-port network out of perfectly reactive elements. In other words, we make our two-port matching network a lossless network. And so we are going to, when we talk about a matching network from now on, we're going to assume that it is a lossless network. Theoretically, we could have a matching network that generates a complex conjugate match that is lossy, but in that case, it wouldn't do as much good, because even though the source is delivering power at equal to its available power, that power is not going to be completely absorbed by the load if the two-port matching network absorbs some of that energy. So when we say matching network here, a lossless device. Now beware. That is, the converse is not true. If we have a lossless network, that does not make it a matching network. We have all the infinite number of lossless networks that we could design. Only one of them will, in fact, act as a matching network for a specific value of ZG and a specific value of ZL. Matching networks are lossless. Most lossless networks, however, are not matching networks. Make sure you understand, matching networks are a tiny subset of the volume of all possible lossless networks. So we need to make our matching networks out of reactive elements. And of course, reactive elements include inductors and capacitors. Later on, we'll find that we can also use links of lossless transmission lines as reactive elements to make matching networks. In that case, basically, the transmission line has inductive and capacitive components, as we'll find out later. So it's still the idea of building the structure out of reactive elements. And so if we go through and we build a lossless two-port network out of reactive elements, then we know the power delivered from the source will be equal to the power absorbed by the load. Again, delivered by the source will be equal to the power absorbed by the load if we have a lossless two-port network. However, in addition to being lossless, if that network is designed to be a matching network, that power delivered from the source will also be equal to its available power. It will be delivering power at the maximum rate possible. And since the device is lossless, then that power delivered will also be absorbed by the load at the other end. A lossless matching network will ensure that all of the available power from the source is delivered, and therefore all of that delivered power is absorbed by the load. Make sure that you understand the logic of that statement. If our two-port device is merely lossless, but not a matching network, yes, all the delivered power will be absorbed since it's lossless, but that delivered power and thus absorbed power will be less, and perhaps far less, than the available power of the source, unless, in addition to being lossless, that two-port device is also a matching network that transforms the load ZL into an input impedance that is numerically equal to the complex conjugate of the source to which it's attached. Now, there's a couple of misconceptions that students have, and I want to address right here. The first one is that a matching network is some sort of plug-and-play device that you can, call up your device vendor and say, send me over a matching network, and you can take that matching network and just drop it in between some source and some load, and magically a conjugate match will occur. That the device somehow looks and figures out what the source impedance is, and then looks and figures out what the load impedance is, and then reconfigures itself in a way such that the load impedance, the specific load impedance, is transformed to the complex conjugate of the source. But that's not how it works. Matching networks are not plug and play. They are designed for a specific load and a specific source. And if you put that matching network between the source and or load that it's not designed for, then you will not get a conjugate match. It's designed for one situation, and you must use it in that situation if you want all the available power of a source to be absorbed by the load. And we can see that with the design equation. Remember, what we're trying to do is transfer a load impedance into an input impedance that's numerically equal to the source impedance, the complex conjugate of the source impedance. And so this really becomes our design equation with respect to the transimpedance parameters now of that lossless matching network. We know the input impedance of a two-port device terminated in some load ZL, or more specifically a lossless two-port device that is connected to a load ZL. We know that input impedance is equal to this. We discovered this earlier. Notice it depends on ZL, as it must, but it also depends on the transimpedance parameters of our lossless device. In other words, it depends on what's inside this blue box of the matching network. We have to design this network, the schematic of this network, such that the transimpedance parameters will satisfy this design equation. We want the input impedance to be numerically equal to the source impedance, whatever that is. Again, that's given. We can't alter that source impedance. All we can do is design what's in the blue box such that the transimpedance parameters satisfy this equation. If the transimpedance parameters of the matching network don't satisfy this equation, they will not create a conjugate match here at the input of the matching network. The input impedance will not be equal to the characteristic impedance, the complex conjugate rather, of the source impedance, unless the transimpedance parameters satisfy this equation. So that's very important. It's not plug and play. If you get a conjugate match and then you change your load, you will no longer have a conjugate match. If you have a conjugate match and you change your source impedance, you will no longer have a conjugate match. It works for one specific load and source together. You change either one of them or both, and you no longer will have all available power absorbed by the load. The second misconception that students have is that the matching network somehow changes the load impedance. That you go through and you put a matching network between a source and a load, and this load impedance will miraculously morph into a new impedance, which happens to be equal to the complex conjugate of ZG. Again, the matching network does not alter ZL. It transforms. We say it transforms, but really what we're saying when we say we transform it is that the resulting input impedance is numerically equal to, let me go back, I think. The resulting input impedance is numerically equal to the complex conjugate of ZG. All right, so ZL is transformed in a way such that the input impedance is equal to the complex conjugate of this. But it's not that somehow the matching network reaches out and changes this impedance ZL into something different. And students often make that mistake. So make sure that you don't. The source and the load are left physically unchanged. We have to design a matching network so that this equation is satisfied. Now, how do we do that? Students ask. Now, that's a topic for another course. It's not particularly hard if we want to do it for one frequency. In fact, if we have just one frequency, we can design a matching network with a single inductor and a single capacitor, two complex elements, and we're done. So it's not particularly difficult to build a matching network, at least a narrowband matching network. Now, having said that, there are some loads where we can't build a matching network, and specifically those are loads that are purely reactive. We cannot build a matching network such that all of the available power of the source will then be absorbed by the load if that load cannot absorb any energy. So if we have a purely reactive ZL, if it's just JXL, there is no matching network that we can design that will extract energy at a rate equal to its available power. In fact, in that case, since the load can't absorb any energy, the source will not deliver any energy. The delivered power will be equal to 0. Generally speaking, when matching networks are discussed, they are always sort of presented and expressed and analyzed in terms of this idea of an impedance transformation, of changing ZL to a new input impedance that's numerically equal to the complex conjugate of the load. But there's an alternate way of thinking about matching networks and what they do. And I think this way is not only equally valid as the impedance transformer, the two together, I think, help students really understand what's going on with respect to conjugate match and matching network. All right, so what we're going to do here is group our matching network, our lossless matching network. And again, I don't say lossless anymore. When I say matching network, it is implied that this is a lossless device. So we have a lossless matching network here, and we're going to pair it with the source itself. So what we're really doing is cutting the port plane between the output of the matching network and the load. And now we're going to consider the equivalent circuit of all of this. And of course, we've done this before. We called this a source transformer. And so if we have a matching network that's designed in the form of a source transformer, what would that matching network do to bring about the condition where all of the available power of this source is ultimately absorbed by that load? So recall what we did before with a source transformation. We start with original source VG and ZG, and then we connect a two-port device in front of it, and that transforms the source into a new source, new Thevenin's source that we call voltage V out and output impedance Z out. So this is simply the equivalent circuit of everything to the left of this port plane. This is the equivalent circuit for the original source with a two-port device attached to it, in this case a lossless matching network. Again, the important thing here to remember is that V out and VG are different complex values, likewise Z out and ZG. The two-port device will essentially transform both of these values, not just the source impedance ZG to Z out. It will likewise transform VG into V out. Once again, I want to point out the mistake or misconception that many students have then when it comes to a source transformation with a lossless two-port network. Again, we transform VG into V out and we transform ZG into Z out. It seems since we transform both of those values to different values that our available power will likewise be transformed. The available power of the transformed source will be different than the available power of the original source. Now that is true if our two-port device is lossless. In that case, the transformed available power will be less. It's also true if the two-port device is active. It's an amplifier. In that case, the available power will likely be greater. But in this case, we're limiting our two-port network to a network that is lossless, that is purely reactive. And we know in this case, and again, this is very important, in a lossless two-port network, even though it will transform both VG and ZG to new values, V out and Z out, it will not alter the available power of that source. The available power of that source is an invariant under transformation with respect to a lossless two-port device. So if the available power is an invariant under transformation, what is it that we want this matching network to do? Well, we start out with our original circuit here, and we know that if we've designed this properly, the lossless network properly, then the delivered power from the source will be equal to its available power. And since then this is lossless, it can't absorb any energy, that delivered power will be ultimately absorbed by this load, the only element that can absorb energy. If we view this matching network, lossless matching network, as a source transformer, we replace all of this with then an equivalent circuit, a Thevenin's equivalent, equal to this. Again, the available power of this transform source is equal to the available power of the original. So what do we want V out and Z out to be equal to? What we're really interested in here is simply the value of Z out. We want to transform our source such that Z out is the complex conjugate of the load impedance. What we're trying to do here is establish a conjugate match, a situation where the load impedance ultimately is equal to the complex conjugate of the source impedance so that it will extract energy from the source at its maximum rate. What is that maximum rate? It's the available power of this equivalent source. But because this matching network is lossless, the available power of this source must be equal to the available power of the original. And so what we find ultimately in this case, then, because we've transformed our original source into a new source such that a conjugate match has been established at the output, we'll pull out energy at a rate equal to the available power of this transformed source, which is equal to the available power of the original source, since this is lossless. This is what we're trying to accomplish now with our lossless matching network. So this last slide I just showed, again, causes confusion among students because it looks like we're saying there what we're trying to do is make the source impedance numerically equal to the complex conjugate of the load. That's exactly what we are wanting to do under that situation. This seems to contradict something we talked about earlier when we talked about, maximum power transfer and optimal impedances, where we said what should the source impedance be such that the power absorbed by the load is maximized. In that case, we said we shouldn't make the conjugate match. We should make the source impedance have a resistive part that is equal to 0. We should make the source impedance as reactive as possible. In other words, remove the resistance. So why don't we do that here? Why are we trying to establish a conjugate match? Well, the reason is that we cannot go through and alter the output impedance and make the resistive value smaller without likewise going through and making the magnitude squared of that voltage source proportionally smaller. Remember, we have a situation where when we transform a source, both the voltage source and the impedance transfer. And they transfer in a way, if it's lossless, such that the available power is conserved. It is an invariant. And so there's, the whole point essentially of going through and trying to reduce the resistive component of the source is to increase the available power of that source. But we cannot increase the available power of the source by attaching a lossless two-port device to it. The available power is invariant. So the best we can do, if we can't change or increase the available power, is just to ensure that all of that available power is absorbed by the load. And we ensure that by applying a conjugate match. And so this procedure that we just did is not in violation of what we talked about earlier. Again, earlier in the class, we talked about what should the source impedance be. We were doing that where we were changing the source impedance while keeping the voltage source fixed. And in that case, the answer was make the available power as large as possible. With a two-port device, again, that's not something we can do. We can't change the source impedance without likewise changing the source voltage in a way that preserves the available power, neither increasing or decreasing it if that two-port device is lossless. Ultimately, if we want to try to increase the available power of our source, we need to attach an active device to it, an amplifier, and that's how we would increase the available power of that source. So from a design standpoint, what we're trying to do with this lossless matching network with respect to source transformation is to go through and transform our original source impedance into a new source impedance that is numerically equal to the complex conjugate of ZL. Really what we're doing is trying to make sure that ZL is the complex conjugate of Z out. And so this becomes our design equation. We need to design a matching network such that the transimpedance parameters of this lossless matching network have the values that will satisfy this equation. If we do that, then the output impedance will be related to the load impedance by complex conjugate. A conjugate match will be established at this port plane, and then all the available power looking to the left will be absorbed by the load looking to the right. Of course, all the available power looking to the left is equal to the available power of the original source, since the matching network is lossless and does not alter that available power under transformation. So once again, the design we have when we do a source transformation is the design for one specific source and load. We have one specific ZG, 10 equal to -3, and one specific ZL, 34 plus J12, something like that, and we need to go through and find the transimpedance parameters then of our design that will satisfy this equation. Once we build that matching network, it will be a matching network, a lossless matching network, to match the original load impedance I said to the original source impedance that I said, but it will only work for that. Again, it's not plug and play. You have to design it for one specific source and one specific load. If you were to change either the source or the load, then you no longer have a conjugate match. You would need to come up with a new matching network. Matching networks are not plug and play. They don't go figure out what they're attached to and reconfigure themselves to ensure that all the available power is absorbed by the load. You have to do the design to ensure that happens. Again, once again, the other thing that matching networks don't do is they don't reach out and change the load impedance into the correct value of the load impedance. They don't change ZG into a value that's the complex conjugate of ZL. ZG remains fixed. Again, what happens, what Z out is the transformed impedance, the equivalent source impedance under transformation when we attach a matching network to it. All right, so don't make that mistake. Again, it's not reaching out and changing the source or load impedance, and it is not a plug and play. You have to design one matching network for one specific matching problem. So you might ask yourselves, which one is better? Should I design a matching network that transforms a source to provide a conjugate match to the load, or should I design a lossless matching network so that it transforms the load into input impedance that's the complex conjugate of the source impedance? And it turns out they're the same, and I mean that very literally. It turns out if we look at this design equation here, which is the one that is for transforming our load impedance into an input impedance, that's the complex conjugate ZG, what we need to do is find a lossless two-port network, again, with these transimpedance parameters that satisfy this equation. This is our design equation that must be satisfied to transform a load impedance into the correct input impedance. If we want to transform our source into a new source whose source impedance is the complex conjugate of our original load, then this becomes the design equation that is extracted. Again, this is the value for Z out under the transformation, and we want that Z out to be equal to the complex conjugate of ZL, and so combining these, we get this result as our design equation. We want to find a two-port device with the transimpedance parameters that satisfy this equation. So it appears that we have two different design equations, one if we're doing a transformation of the source and the other if we're doing a transformation of the load. And so it appears that we could have two different designs. But if we look at it, we find that those two design equations are the same design equation. If we start with our first design equation here for trying to transform our load into the proper input impedance, we take the complex conjugate of both sides and then solve for the complex conjugate, or solve for the complex conjugate ZL, then we get this result. And this is precisely the design equation we had for the source transformer. And so we show that those two equations, the design equations, are in fact the same design equation. What this means is that if we design a lossless matching network which transforms our load impedance into a new input impedance, which is the complex conjugate of the source. In other words, we establish a conjugate match at the input to the matching network, a conjugate match at the output of the source. It is likewise a matching network that will transform the source now to a new source impedance that applies a conjugate match at the output of the matching network at the input to our load. That two-port matching network, the lossless two-port matching network that results, will create a conjugate match at both ports. However we look at it, however we come up with an equivalent circuit, if we draw a line for the input and then come up with an equivalent circuit left or right, we would find that they're related by conjugate match. If we look at the port plane at the output of the matching network just before the load and we come up with an equivalent circuit left or right, once again we would find that there's a conjugate match looking both left and right. Now, the impedances are going to be different, either from the output plane, port plane, or the input port plane, but in both cases there will be a conjugate match that occurs. So it turns out that a lossless matching network that transforms a load impedance into the correct input impedance, such we have a conjugate match, is precisely the same two-port device that will transform a source into a new source, such that there's a conjugate match on the output. So when it comes to designing a lossless matching network, you can use either design equation. You can try to establish a conjugate match here, or you can try to determine a conjugate match at this point. And it doesn't matter because the design you come up with will be precisely the same in either case. If you establish a conjugate match here by transforming the source into a new source, we'll find that there's a conjugate match here, and the same two-port lossless matching network transforms our load into a new input impedance, which is the complex conjugate here. If you establish a conjugate match at one place, that means you've established it at the other place as well simultaneously. So when it comes to design, you can pick either equation. You can think of it either way. Whatever one is more comfortable to you, whichever one is easier to solve, it doesn't matter. Again, they are equivalent. Designs are going to be exactly the same, the result. And so the term that a lot of times engineers use for things like this is, you can argue that one design approach is like saying a checkerboard is a red board with black squares, or you can say a checkerboard is a blackboard with red squares. It doesn't really matter. Either statement is precisely correct in terms of describing a checkerboard. Likewise, when it comes to matching lossless matching networks and source or load transformation, it doesn't matter how you describe what you did, you will come up with the same result. So there's a very important point to make then, and one that's important to keep in mind in this class. And we can use this over and over again to great effect if we really understand what we're saying. If we have a lossless matching network between a source and a load, it means that we have a conjugate match at the output of the source. In other words, the input impedance looking one way is the complex conjugate of this source, which means all the power delivered by this source all the power available from this source is going to be delivered. But since this lossless matching network is lossless, all of that delivered power will be ultimately absorbed by the load. We have what we want, all of the available power being delivered and all of that delivered power being absorbed. And that will occur if we have a conjugate match here at this port. It will likewise occur if we have a conjugate match at this port. So we look at this and the available power looking left for the equivalent source here. All right. If we have a conjugate match, all of that available power will be delivered. But of course, the available power of this transform source is the available power of the original source. And since all that available power is delivered by this transform source, then it will be absorbed directly by this load. Once again, we have the ideal situation. All the power absorbed by the load is equal to the available power of the original source. Again, it's important to understand if we have a lossless matching network, these two things happen simultaneously. If I have a conjugate match here, I have a conjugate match here. What it means is if I have a conjugate match at any place, I actually could go through and saw my matching network in half and come up with an equivalent circuit looking to the left, an equivalent circuit looking to the right, an equivalent source impedance looking left, and an equivalent input impedance looking right. And if those two impedances are related by complex conjugate, then I have a conjugate match. All of the available power of the original source will be absorbed by the load at the end. So it doesn't matter where we establish a conjugate match, all available power of the source will be absorbed by the load. And that means that if we establish a conjugate match at one spot, we have a conjugate match at every spot. And this is very important from a circuit analysis. If I go through and I say I have a circuit and all the available power from the source is being absorbed by that load, what does that tell you? That means we have a conjugate match. Where? Everywhere. I could slice the circuit this way and look at the source impedance, equivalent source impedance looking left, and the input impedance looking right, and they'll be related by complex conjugate. If I slice it here at the end, and I come up with the equivalent circuit looking left and the equivalent circuit looking right, and I compare the two, source impedance to load impedance, I'll find they're related by complex conjugate. Again, I could cut this circuit right through the matching network and come up with an equivalent source looking left and an equivalent load looking right. Once again, the impedances would be related by complex conjugate match. If all available power of the source is absorbed by the load, there is a complex conjugate match everywhere, which means if there's a complex conjugate match anywhere, there's a complex conjugate match everywhere, and all the available power of the source is absorbed by the load. Make sure you understand how that all fits together. This is very important in this class, is once you have one thing, a string of things happen. Now again, one more warning, and listen to this. This is true if this two-port network is a lossless matching network. Not a lossless network. Most lossless networks are not a matching network. Most lossless networks are not going to solve those design equations. So it's not enough to have a lossless network there. All the lossless network does is ensure that the delivered power is equal to the absorbed power, but that delivered power could be a tiny fraction of the available power. If I want all of the available power to be absorbed by the load, I need not only a lossless network, I need a specifically designed network for that situation that we call a lossless matching network. Again, of all the two-port networks that are lossless, we have one little dot, which is the matching network for a particular source and load. Almost all lossless networks are not matching networks. All right, so make sure that you don't get those two confused. A big mistake in this class, students make them synonymous. Oh, every lossless network is a matching network. No, only one of all possible lossless networks is a matching network for a given source and load.